The standard error is the standard deviation of the sampling distribution of a statistic. The term may also be used to refer to an estimate of that standard deviation, derived from a particular sample used to compute the estimate. For example, the sample mean is the usual estimator of a population mean. However, different samples drawn from that same population would in general have different values of the sample mean, so there is a distribution of sampled means. The standard error of the mean is the standard deviation of those sample means over all possible samples drawn from the population. Secondly, the standard error of the mean can refer to an estimate of that standard deviation, computed from the sample of data being analyzed at the time. In regression analysis, the term standard error is also used in the phrase standard error of the regression to mean the ordinary least squares estimate of the standard deviation of the underlying errors. Standard error of the mean. The standard error of the mean is the standard deviation of the sample means estimate of the population mean. SEM is usually estimated by the sample estimate of the population standard deviation divided by the square root of the sample size, where S is the sample standard deviation, and N is the size of the sample. This estimate may be compared with a formula for the true standard deviation of the sample mean, where I florin is the standard deviation of the population. This formula may be derived from what we know about the variance of a sum of independent random variables. If our independent observations from a population that has a mean and standard deviation, then the variance of the total is the variance of must be, and the standard deviation of must be, of course, is the sample mean. Note: the standard error and the standard deviation of small samples tend to systematically underestimate the population standard error and deviations. The standard error of the mean is a biased estimator of the population standard error. With n equals 2 the underestimate is about 25%, but for n equals 6 the underestimate is only 5%. Gerland and Troepathy provide a correction and equation for this effect. Sokol and Rolf give an equation of the correction factor for small samples often R20. See unbiased estimation of standard deviation for further discussion. A practical result, decreasing the uncertainty in a mean value estimate by a factor of 2 requires acquiring 4 times as many observations in the sample. Or decreasing standard error by a factor of 10 requires 100 times as many observations. Student approximation. When I-florin value is unknown, in practical applications, the true value of the I-florin value is unknown. As a result, we need to use an approximation of the Gaussian sample distribution. In this application the standard error is the standard deviation of a t-student distribution. T-distributions are slightly different from the Gaussian, and vary depending on the size of the sample. To estimate the standard error of a t-student distribution it is sufficient to use the sample standard deviation S instead of I-florin, and we could use this value to calculate confidence intervals. Note: the student's probability distribution is a good approximation of the Gaussian when the sample size is over 100. Assumptions and usage. If the data are assumed to be normally distributed, quantiles of the normal distribution and a sample mean and standard error can be used to calculate approximate confidence intervals for the mean. The following expressions can be used to calculate the upper and lower 95% confidence limits, where is equal to the sample mean, is equal to the standard error for the sample mean, and 1.96 is the 0.975 quantile of the normal distribution, upper 95% limit and lower 95% limit. In particular, the standard error of a sample statistic is the estimated standard deviation of the error in the process by which it was generated. In other words, it is the standard deviation of the sampling distribution of the sample statistic. The notation for standard error can be any one of SE, SEM, or SE. Standard errors provide simple measures of uncertainty in a value and are often used because, if the standard error of several individual quantities is known then the standard error of some function of the quantities can be easily calculated in many cases. Where the probability distribution of the value is known, it can be used to calculate a good approximation to an exact confidence interval. And, where the probability distribution is unknown, Relationships like Chebyshev's or the Vysotsky-Petunin inequality can be used to calculate a conservative confidence interval. As the sample size tends to infinity, the central limit theorem guarantees that the sampling distribution of the mean is asymptotically normal. Standard error of mean versus standard deviation. In scientific and technical literature, experimental data is often summarized either using the mean and standard deviation or the mean with the standard error. This often leads to confusion about their interchangeability. However, the mean and standard deviation are descriptive statistics, whereas the standard error of the mean describes bounds on a random sampling process. Despite the small difference in equations for the standard deviation and the standard error, this small difference changes the meaning of what is being reported from a description of the variation in measurements to a probabilistic statement about how the number of samples will provide a better bound on estimates of the population mean, in light of the central limit theorem. Put simply, the standard error of the sample is an estimate of how far the sample mean is likely to be from the population mean, whereas the standard deviation of the sample is the degree to which individuals within the sample differ from the sample mean. If the population standard deviation is finite, the standard error of the sample will tend to zero with increasing sample size, because the estimate of the population mean will improve, while the standard deviation of the sample will tend to the population standard deviation as the sample size increases. Correction for finite population. The formula given above for the standard error assumes that the sample size is much smaller than the population size, so that the population can be considered to be effectively infinite in size. This is usually the case even with finite populations, because most of the time, people are primarily interested in managing the processes that created the existing finite population. This is called an analytic study, following W. Edwards Deming. If people are interested in managing an existing finite population that will not change over time, then it is necessary to adjust for the population size. This is called an enumerative study. When the sampling fraction is large in an enumerative study, the estimate of the error must be corrected by multiplying by a finite population correction. To account for the added precision gained by sampling close to a larger percentage of the population. The effect of the FPC is that the error becomes zero when the sample size n is equal to the population size n, correction for correlation in the sample. If values of the measured quantity A are not statistically independent but have been obtained from known locations in parameter space X, an unbiased estimate of the true standard error of the mean may be obtained by multiplying the calculated standard error of the sample by the factor f. Where the sample bias coefficient I is the widely used Praswinson estimate of the autocorrelation coefficient for all sample point pairs. This approximate formula is for moderate to large sample sizes. The reference gives the exact formulas for any sample size, and can be applied to heavily autocorrelated time series like Wall Street stock quotes. Moreover, this formula works for positive and negative I alike. See also unbiased estimation of standard deviation for more discussion. Relative standard error. The relative standard error is simply the standard error divided by the mean and expressed as a percentage. For example, consider two surveys of household income that both result in a sample mean of $50,000. If one survey has a standard error of $10,000 and the other has a standard error of $5,000, then the relative standard errors are 20% and 10% respectively. The survey with a lower relative standard error has a more precise measurement since there is less variance around the mean. In fact, data organizations often set reliability standards that their data must reach before publication. For example, the U.S. National Center for Health Statistics typically does not report an estimate if the relative standard error exceeds 30%. See also, coefficient of variation, illustration of the central limit theorem, probable error, sample mean and sample covariance, variance, references.